All right, welcome back from lunch. So this is part 2 of this adventure, which is now I'm actually going to put my Intel hat on. I am now an Intel reliability principal engineer. And what I'm going to talk about is a little bit how Intel approached looking at the thermochemical reliability of components in immersion solutions, specifically looking at doing a risk assessment against some packaged materials that we had for Ice Lake and POW 6. I'm going to use this as an example. But what I'm also going to give you is the process, the process flow we went through, how we thought about this process, how we used the data, how we assimilated all this data, and did it in a very methodical way so that we made this as efficient as possible by leveraging as much as our existing data that we had. Because we all know, as a component supplier, we have a really robust thermomechanical qualification baseline. So in this case, we wanted to use that as sort of the foundational work and use that data, but yet add on the thermochemical reliability. So, again, for those of you that were in my previous one, I wanted to revisit this concept of thermochemical quality and reliability. Again, this is a new terminology that we're really communicating within the community, especially with immersion, is thermochemical quality, material incompatibilities. Thermochemical reliability is the incompatibilities that then impact your fluid. So we want to look at both of those as a function of what is the overall reliability of a component within an immersion solution, because the immersion solution has more than just a single component. It is an entire solution. So the way we approach this at Intel is we did this in a very stepwise approach. So the first thing we did is we did an FMEA. How many engineers have done an FMEA? Failure modes engineering analysis. Exactly. Very efficient process to say, what should I actually care about? So we did that specifically for thermochemical failure modes. We then moved into component material compatibility to address some of those FMEA risks. We then moved into component thermochemical reliability to understand if those component material compatibility risks translated to reliability risks. We then aggregated it at the system level to say, okay, we understand the thermochemical reliability of the component in a clean, neat fluid, but what is it now that we have the system level risks? And then all of that combined into a reliability risk assessment for the component in a representative set of system ingredients. So the first thing we did is our thermochemical FMEA. So what we did is compiled a list of our component materials. Again, our packages have a wide variety of materials, very complex materials, many of which I can't even talk about what they are. But what we did is we specifically went through all of those materials. What is the function of that material? And what are potentially the failure modes that could result from a material incompatibility of that specific material with that package? Is it a thermal failure? Is it an electrical failure? And do those particular failures result in a reliability risk? We then went through the FME and graded all of the reliability risks. And of course, the higher reliability risks floated to the top of the table. We then identified the component compatibility risks that could result in an unacceptable reliability risk for our components and our customers that are trying to deploy these components in immersion solutions. And the example I'm going to keep using throughout this process is a particular package material that I'm going to call polymer S. Again, we have multiple polymers in these packages, but I'm going to call polymer S, and its specific function has a very specific thermal reliability function. And if we saw either delamination of polymer S due to degradation in mechanical properties, or we saw the delamination from the material swelling, both of these would result in a high reliability risk of the package. So we went through and said, okay, we need to understand what is the response of this polymer to the fluid. So then we went into material compatibility testing of the component. We defined a test plan to collect the data on these critical material properties. So again, looking at this property, what are the critical material property functions within that package? And we specifically did a test plan looking for those specific failure modes. We executed the material compatibility, and then we analyzed the data to determine if the post-soak properties were statistically worse than our control baseline. So when we did this testing, and this is our actual data, by the way, on this specific polymer material, and we had our control baseline, and we had our POW 6 baseline. So after we did the soak testing of polymer S, we did see that there was a statistically different difference in the ultimate tensile strength of this material. We also saw that the loss tangent had a much different behavior and a degradation in the loss tangent behavior of this material after the soak procedure. So we said, okay, this risk is realized. We do see a degradation in mechanical performance of this critical material that could result in a reliability risk. We also did, we also looked and said, okay, we saw a material swelling change, and we said, okay, we did a weight change. We saw the weight change. Now, can we confirm that the POW 6 is actually absorbing into the material? And in this case, we did. So we say, okay, we've got two of our risks realized where we see a degradation of mechanical properties and we see that the material is swelling due to influx of POW6 into this particular material in our package materials. So then we're like, okay, do these material compatibility changes result in a reliability risk? So then we now had to go address a thermochemical quality and reliability plan. So essentially we needed to measure our package component, our opponent, to ensure component meets our acceptance criteria. So before you even dunk it, does it work? Does it meet your performance standard? Does it meet your post-manufacturing spec standard? We then soaked it in immersion fluid. In this case, we used our thermomechanical baseline. So we had a very robust thermomechanical baseline. We understood what those temperature time conditions are. We had a full reliability model for that. So the way we approached it is said that any change from our thermomechanical baseline that is statistically different due to being immersed in fluid would be the thermochemical component. So if you have no changes due to your thermochemical reliability modes, you should see something that's statistically matched from your thermomechanical baseline. So we use the same time as our air baseline or our control baseline, and we use the same temp as our material compatibility testing. So again, we leveraged it to say we're going to test that same material response, but we're going to do it with the time using our thermomechanical time baseline. We measured the component performance after soak, and then we determined if the performance after the soak was statistically worse than the baseline. And when we did this, specifically for our junction to case thermal resistance, which for this failure mode was what we were measuring, what we did observe in this case was for the time that we tested against our thermomechanical baseline and for our existing results, we did not see actually a statistically different response in the junction to case thermal resistance after these pokages were soaked for the same period of time that we would do for our thermomechanical baseline. So this was actually a really positive result for us. We didn't see a risk with these test vehicles. But this was the results in the clean POW6. It did not account for all of the other things that are going on within the system. So then we had to take the next step, which was system thermochemical reliability. Now that we know that there's not a fundamental reliability risk of the package material of polymer S with neat POW6, is there a risk because of all the contamination that other system ingredients produce to the viscoelastic material? Does it get worse, right? So we took these systems and we eliminated critical material incompatibilities from our test systems. And these were actually Intel systems. These were Intel Ice Lake Coyote Pass systems. We did a full material compatibility. We basically broke the whole thing apart and we did each component individually. And yes, we found things that were atrociously bad and we had to actually do replacements at the last minute because the server was built to go in air, not immersion. So we eliminated all the critical material incompatibilities from these test systems. We deployed a full rack weather, so 24 systems into this tank in POW6. These were spread core systems, again, third generation Xeon, and we basically deployed all 24 in full rack configuration. We measured the performance of the CPUs, and we used, again, PTAT, which I think any of you guys use Intel Xeon. It's our standard thermal performance profile where it measures the performance of the CPU with a very specific workload. So we did PTAT beforehand and said, okay, we have a T0 baseline and with neat, as close as we can to neat fluid. What is the performance and does it meet our requirements, which it did. We then looked at this and modeled this system as an ideal batch reactor. And we did that, and these are pretty decent use case assumptions because if you talk to customers and how they deploy these particular systems, they say, I'm gonna have a tank, I'm gonna have the fluid, and I'm gonna have these systems, and my intent is to never change any of it. So in all intents and purposes, we can treat this as a closed system. And the other assumption that the system's well mixed, that's pretty reasonable. I mean, the fluid's constantly circulating. Is it a perfect assumption? No. Is it a reasonable assumption? Yes. So then if you say, okay, I have all these contaminants that are being introduced, then you get a steady state assumption where at some point in time, any of these secondary reactions are gonna equal out. And you're gonna sort of get a stable contamination rate as a function of time. And it's gonna stabilize. And at this point in time, it shouldn't change all that much for the use case lifetime of these systems. And that could be modeled as the reasonable risk for the service lifetime of these solutions for their service lifetime for their contamination levels. And what we had to prove is that we could monitor the actual contamination level as a function of time, and we did that. And we did this with a really easy technique called UV-Vis. And what we did is we just took samples over time, and we basically proved that the contamination actually does saturate at a period of time, and then it sort of stabilizes. So this was critical. Like, yes, it does saturate, and yes, it does stabilize. So then we can kind of envelope as the contamination use case. We then measured the component performance after the contamination saturation was achieved, and we said, okay, before, at that T0, before we did the saturation and after, did we see a change, a statistically different change in the PTAT workload as a function of the contamination levels? And in this case, what this is showing is we didn't. So if we did what we call delta T, which is the temperature, the DTS sensor minus the inlet before and after, we didn't see a statistically different change. So for the contamination levels that we measured, and yes, we did do a thorough analysis of what this contamination is, and that is outside the scope of this presentation. But for the contamination levels that we achieved here, we didn't see a statistically different, what was that look for? I'm seeing him wince over here. I'm like, what? Blame him for being the distraction. So we didn't see a statistically different response in these CPUs, which was an incredibly positive response. So we actually proved, when you look at this and we combine all this data, we then said, okay, now we got to take all this data we collected and say, what's the thermochemical reliability risk assessment? So we took the component material compatibility, the component reliability, and the system reliability analysis, and we combined all of that to create what we're calling the thermochemical reliability risk assessment in PAL-6. So if you consolidate all that data, so component compatibility, we saw the decrease in mechanical properties of polymer S. We saw the swelling from polymer S. However, when we did the reliability testing, the thermal performance for this particular fluid was matched to the air baseline after the immersion soak. And when we did the system reliability, we didn't see a statistically different performance of our CPUs between neat PAL at T0 and the saturated contaminated PAL at the end of our testing. So therefore, what we ended up doing is saying the reliability risk for this particular material, which is a polymer S, for these thermal failure modes is actually low. So this was actually really, I think, the first of kind. It was positive, and this was actually the foundational data that we used to make a reliability risk assessment for our third generation CPUs in PAL-6 for very specific customers. So how do we use this data? How do we use this methodology to, and how is Intel using this to help lead the community as a leader, or as saying, hey, look, we developed all of this. How do we use this to actually build a community where we have immersion solutions and we can standardize some of these things together? And one of the things that we really need to do is execute thermochemical reliability testing on ITE components. So we did this on our CPU, but as you say, there's still this one big open risk in our brain, is that we have seen in certain fluids that the contamination can cause failures. So any of the failures that we've seen that customers have worked with us on, it's not necessarily due to fundamental incompatibilities of our package materials. It's been from reactions of other things that shouldn't be there. So this reduction of contamination is really necessary for the entire ecosystem to have reliable servers. We all have to work together. Every component vendor out there, every fluid vendor out there has to take it as an initiative to say, you know, we all have to be good citizens to each other when we're talking about being successful in immersion. And we all have to say, I have to do everything I can to reduce the contamination that my materials are releasing into the fluid. Because even though you have one particular contaminant, it may not be a problem, but if it decides it wants to react with something else, it could be a problem. And this means that as component vendors, we have to consider and implement strategic material changes to improve the thermochemical reliability of components. Specifically, sometimes you have to make changes to make it more reliable for the fundamental material compatibility, but sometimes you may have to make changes to say, okay, I'm not going to release as much contamination into the fluid. And these things, you know, we even did this on a couple of our things to say, okay, we can make small changes and it will improve things. Consider and implement strategic material or process changes to reduce the contamination and participate in the work streams. Again, this is an example of how we can, you know, work as a team to provide guidance through the standardization. This is what we did. This is what we've done. But we need an ecosystem to say we're all doing this together, we're all testing together, because again, the big gap still is I can do this in one fluid, I can do this for a neat fluid, but I still have this unknown risk of what everybody else is doing to influence the reliability of my component in a contaminated fluid. So please, if you're a component vendor, if you're a fluid vendor, if you are an ODM, we need to hear from you. We need you to participate and say, what do you need? What kind of data do you need? What kind of testing do you need? What kind of standardized testing methodologies can we develop together so that we can develop more reliable solutions where we're all working together to be good citizens for each other? And I also want to say thank you. It took an incredible team at Intel to support this work. I do want to acknowledge all of the people that contributed to collecting this data as well. And I'll take any questions. And I actually have time to answer them. I was worried I wasn't going to get through this in 20 minutes. So.
Samantha, I think some people have like a very quick way they think about material compatibility, and they think expensive materials are more compatible. Or another way to put it is compatible materials are more expensive. I don't want you to make any IP claims or anything, but is that really true? I mean, do you think that's that? Because same thing. It has this myth of, well, we're trying to save money, so we got a component that's a bad citizen in the immersion tank.
I think that the cost question comes up is that if your current component that you have a baseline on, that you're comfortable with, that you have an ecosystem, and that you have your supply chain supports, and it is expensive and time-consuming, and it's not easy sometimes to switch components, and it does cost time, money, and effort to switch out some of these components, especially if you're working with downstream suppliers. And I have to acknowledge that that is extremely difficult for us. And that's why we have to, if we're looking at the ecosystem and the 4-year lead, it takes up to that long. Or if you can't make any changes with your components that are currently on your roadmap, how about your future-looking products? We're all in this product development cycle where we, have products going 2 years out, 3 years out. So can we make conscious decisions as an ecosystem to say, well, I know my current products aren't compatible, and I know these are the reasons why they're not compatible, but for my future products, can I make strategic changes so when I qualify that new product, it is now more compatible because I have changed it, but I'm not going back and repeating the qualification of my previous product. So I think it's going to be a combination of all these solutions, depending on cost and schedule goals, but I think that we need to look at all these different options. One of the first things we have to do is say, how do we just test it? How do we test to make sure it is or is not compatible? Please.
Excuse me. Sorry. So could you talk a little bit more about, during your test, what's the chemistry of those contaminations?
I'm sorry, what's the?
The chemistry, and what type of major species there to contaminate the oil?
What kind of contaminants are in there?
Yeah.
Primarily phthalates, because again, we have a lot of cables, and solder, the solder pastes, the glycol ethers. We also saw a little bit of metal contamination. But we were able, actually, going back to making strategic changes, is that, some of the solder paste for the low-temp solder for heat sinks. So we developed the heat sink, the immersion heat sink that we deployed in these systems, and it turns out when we did the material compatibility testing, that solder paste that they were using to solder together that heat sink was putting off an awful lot of, it was like this brown goo that was just seeping out of the heat sink. It looked disgusting. So we ended up having to go work with our heatsink supplier and say, okay, you're gonna have to change your solder paste. They had to change the solder paste for us 3 times to find one that passed our material compatibility guidance. And yeah, that took time, effort, and yeah, our heatsink supplier was like rolling their eyes at us. But yeah, that's what I have to say is those are the types of things, and that's why you have to do the individual component level material compatibility, is because that's your one opportunity to say, can I make a strategic change for this single component to make my whole system material compatibility improve.
Yeah, thanks for sharing.
Yeah.
So in your example where you used the soak test, for that test and abstracting a step forward, should the coupon or whatever you're using, should that be at an operational state, or are you just doing a passive soak?
That's the next step. So this time, going back to an incremental, a lot of these methodologies did not exist when we started this. So the way I've approached it with my team is I take very much an incremental, and you'll see me with an OCP do this, is that I'm getting kicked off stage again. To answer your question is that this was done in a non-op, but I am now doing things in an op state. And that, yes, the risks are different.